Good day, today we're going to discuss and demonstrate Bernoulli's principle, specifically Bernoulli's equation with no friction losses. Now before we start, let me present the objectives of our report. First, to understand the principles behind Bernoulli's equation. Next, to derive and explain Bernoulli's equation. Then, to recognize the assumptions and limitations of Bernoulli's equation in ideal scenarios. And lastly, to apply and solve problems using Bernoulli's equation to various fluid mechanics problems. Now, without further ado, let's start the discussion. What we can see here is a tube. Reading the text underneath it, it says that when a tube narrows, the same volume occupies in a greater length. For the same volume to pass points 1 and 2 in a given time, the speed must be greater at point 2. The process is exactly reversible if the fluid flows in the opposite direction. Its speed decreases when the tube widens. Note that the relative volume of the two cylinders and the corresponding velocity vector arrows are not drawn to scale. Hence, when a fluid flows into a narrower channel, its speed increases. That means its kinetic energy also increases. The increased kinetic energy comes from the net work done on the fluid to push it into the channel. Also, if the fluid changes in vertical position, the work is done on the fluid by gravitational force. A pressure difference occurs when the channel narrows. This pressure difference results in a net force on the fluid because we know that pressure times the area equals force. And this net force does the work. On our next slide, we can see here Bernoulli's principle. So, Bernoulli's principle can be stated as follows. 1. As the speed of fluid increases, the pressure decreases. And 2. Conversely, as the speed of the fluid decreases, the pressure increases. Now, here we see a diagram of a pipeline with a fluid flowing through it. This could either be a liquid or a gas. And we're going to assume that the rate of flow is constant throughout the system. If we assume that the rate of flow is constant, then that means where the cross-sectional area is smaller, it tends to move faster to get through. So, we've got a low velocity region and a high velocity region. Then going back to a low velocity region because this is a Bernoulli tube. Now, Bernoulli's principle tells us that when we go from a low velocity high pressure to a higher velocity, that the pressure will drop and the low pressure, and then one would go back to a lower velocity again, the pressure will increase. So, Bernoulli's principle states that for an incompressible frictionless fluid, the total mechanical energy of the fluid remains constant along a streamline. This total mechanical energy is the sum of the pressure energy, kinetic energy due to the velocity, and potential energy due to the elevation. And that leads us to our next slide, which are the basic fluid dynamics concept: pressure, velocity, and elevation. I believe that this will be further discussed in the following slides, so here's a brief introduction. Pressure. We know that pressure is the force exerted per unit area by a fluid. Now, in fluid dynamics, pressure can vary along the flow of the fluid and plays a crucial role in determining the behavior of the fluid. Next, we have here velocity. Velocity is the speed and direction at which fluid particles are moving. In a flowing fluid, velocity can change from one point to another. Now, lastly, we have here elevation. Elevation is the height above a reference point, often considered the potential energy per unit volume due to gravity in a fluid system. Higher elevation means higher potential energy. Now, to demonstrate Bernoulli's principle with no friction loss, we have here two pieces of paper. Now, what my groupmate will do is to hold the papers vertically and blow air between them. We notice that the two papers come together. Hence, by blowing some high-velocity air between the two pieces of paper, that will reduce the pressure in between, and the atmospheric pressure will then tend to push them together. according to Bernoulli's principle, an increase in the velocity of the fluid, air in this case, in our experiment, results in a decrease in the pressure. So to summarize our experiment, blowing air between the papers increases the air velocity, decreasing the pressure between them due to Bernoulli's principle. The higher pressure on the outside of the paper pushes them together, demonstrating the inverse relationship between fluid velocity and pressure. Now let's have a brief history. I know that I kept on rambling about Bernoulli, but who introduced us Bernoulli's principle? Bernoulli's principle is introduced to us by Daniel Bernoulli. So Daniel Bernoulli was born in February 8th, 1700s in Groningen, Netherlands, and unfortunately died in March 17, 1782 in Basel, Switzerland. Daniel Bernoulli was a prominent member of the second generation of illustrious Bernoulli family of Swiss mathematicians. His contributions spanned a variety of disciplines, including mathematics, medicine, biology, physiology, mechanics, physics, astronomy, and oceanography. And he is best known for what we're discussing now, which is the Bernoulli's theorem that bears his name. Daniel Bernoulli was Johann Bernoulli's second son, and it was Johann who initially introduced him to mathematics. After pursuing studies in philosophy, logic, and medicine at the universities of Heidelberg, Strasbourg, and Basel, Daniel earned his MD in 1721, between 1723 and 1724. And then he authored Exercitationes Quaedam Mathematica, which dealt with differential equations and physics of fluid flow. This work led to his appointment at the prestigious Academy of Sciences in St. Petersburg, Russia. There, he lectured on medicine, mechanics, and physics until 1732, conducting research on the properties of vibrating and rotating bodies and contributing to the field of probability theory. In 1732, he returned to the University of Basel to take up a position in anatomy and botany. By this time, he had earned the respect of scholars and was admired by the public across Europe. Daniel Bernoulli gained prominence in 1738 with his work Hydronomica, where he examined crucial properties of fluid flow such as pressure, density, and velocity, and described their fundamental relationship. In this work, he introduced Bernoulli's principle, which states that the pressure decreases as velocity increases. Additionally, he laid the groundwork for kinetic theory of gases and heat, showing that the pressure on the surface is due to molecular impacts and that the pressure and motion increase with temperature under the assumption of constant random molecular motion. Around the same time, his father, Johann, published Hydraulica in an attempt to claim priority over his son's findings, highlighting his ongoing antagonism towards Daniel. So from 1725 to 1749, Daniel won 10 prizes from Paris Academy and Sciences for his work on astronomy, gravity, tides, magnetism, ocean currents, and the behavior of ships at the sea. He also made significant contributions to probability theory in 1735. He shared a prize with his father for work on planetary orbits, an event that reportedly led to Johann expelling him from the house out of jealousy. Now, Daniel's award-winning papers showcased his ability to tackle cutting-edge scientific problems and effectively communicate them to the public in 1732. He accepted a position in botany and anatomy at Basel, followed by a physiology in 1743, and later a position in physics in 1750. That's all. Thank you. Next reporter, please.
Bernoulli's equation is a fundamental principle in fluid dynamics that describes the conservation of mechanical energy in a flowing fluid. This equation links the pressure, velocity, and height of a fluid in steady, incompressible, and non-viscous flow. The equation is a statement of the conservation of mechanical energy for the fluid flow, considering the following three forms of energy per unit volume. So first is the pressure energy. Pressure energy is the energy stored in a fluid due to its pressure. It represents the potential energy per unit volume available due to fluid pressure. It can be likened to potential energy stored in a compressed spring. The higher the pressure, the more energy is stored in the fluid. It is expressed as P, where P is the pressure of the fluid. Next is kinetic energy. Kinetic energy in a fluid is the energy due to its motion or velocity. Kinetic energy increases with the square of the fluid velocity, meaning small increases in velocity result in significant changes in kinetic energy. It is expressed as 1/2 mv squared, where m is equal to the mass and v is equal to the velocity of the fluid. Next is potential energy. Potential energy in a fluid refers to the energy associated with the fluid's height in a gravitational field. It is expressed as mgh, where m is equal to the mass, g is equal to the gravitational field strength, and h is equal to the height. Here are the key assumptions. First is steady flow. In fluid dynamics, steady flow refers to a situation where the fluid properties at any given point do not change with time. This means that variables such as velocity, pressure, and density remain constant at any specific location within the flow field over time. Example is flow of water in a straight, constant diameter pipe. So, considering the flow of water in a straight, constant diameter pipe, if the flow rate is steady, the velocity of the water at any given point in the pipe does not change over time. Thus, if you were to measure the velocity at a specific point within the pipe, you would find the same value regardless of when you take the measurement, provided the flow remains steady. Next is incompressible fluid. An incompressible fluid is one whose density remains constant regardless of changes in pressure or flow conditions. This means that the volume of the fluid does not change significantly under compression or expansion. So example is water. Liquids like water are often treated as incompressible because their density changes very little with variations in pressure and temperature under typical conditions. For an ideal fluid, Bernoulli's equation can be applied to describe the relationship between the pressure, velocity, and elevation along a streamline. It states that in a steady ideal fluid flow, the sum of the pressure energy, kinetic energy, and potential energy per unit volume is constant along any streamline. This equation is foundational in fluid mechanics and is used to analyze the behavior of fluids in various practical and theoretical scenarios, providing insights into fluid dynamics and engineering applications. Example, when modeling fluid flow in pipes, water is sometimes treated as an ideal fluid to understand the basic flow characteristic without the complications of frictional forces. This idealization helps in deriving primary relationship like the Hagen-Poiseuille equation. When we talk about flow along a streamline, we mean the flow of a fluid along a path where the velocity vector at every point is tangent to the streamline. Bernoulli's equation, which describes the conservation of energy in a fluid flow, applies strictly to points that lie along the same straight line. This equation states that the total mechanical energy per unit mass of the fluid remains constant along a streamline, assuming the fluid is non-viscous, incompressible, and there are no external forces acting on it except for gravity. So for example, in a river, water particles follow different streamlines, and Bernoulli's equation can be applied to each streamline separately. Bernoulli's equation helps in understanding how the flow velocity and pressure vary as water moves through different sections of the river. For instance, near the surface where the flow velocity is typically higher due to reduced friction, the pressure is lower compared to deeper parts of the river. These variations in pressure and velocity can influence the distribution of forces and turbulence within the river.
So now let's discuss about the limitations and practical considerations. So When a fluid flows, energy is expended to overcome the resistance caused by viscosity. This energy is transformed into heat due to the internal friction between fluid layers. As a result, the total energy of the system decreases, leading to a loss of mechanical energy. In terms of Bernoulli's equation, which describes the conservation of energy along a streamline in a fluid flow, the presence of viscosity introduces additional energy dissipation not accounted for in the idealized implicit case. In real-world applications where viscosity cannot be neglected, Bernoulli's equation becomes less accurate. The energy losses due to the viscosity alter the distribution of energy within the fluid, affecting pressure and velocity profiles along the flow path. So, for example, consider the flow of oil through a pipe. Oil typically exhibits a significant viscosity compared to other fluids like water or air. As the oil flows through the pipe, it experiences resistance from the pipe walls and encounters internal friction between its layers. This viscosity causes energy dissipation in the form of heat. Therefore, when analyzing the flow of oil using Bernoulli's equation, the effects of viscosity must be taken into account to obtain accurate. So next limitation is the turbulent flow. So turbulent flow is characterized by chaotic and irregular fluid motion, where velocity and pressure fluctuate rapidly and unpredictably in both magnitude and direction. In turbulent flow, the edges and vertices form and interact with each other, creating a highly complex flow pattern. This chaotic behavior distinguishes turbulent flow from laminar flow, which is smooth and orderly. Bernoulli's equation is based on the principles of conservation of energy along a streamline, hence derived under the assumption of laminar flow. It assumes that the fluid moves smoothly with negligible viscosity and turbulence. However, in turbulent flow, the presence of chaotic motion and rapid fluctuations in velocity and pressure invalidate this assumption. As a result, Bernoulli's equation becomes less accurate for describing turbulent flow conditions. So, for example, airflow over an airplane wing can transition from laminar to turbulent under a certain condition, such as at high angles of attack or during turbulent atmospheric conditions. In the case of high angles of attack where the flow separates from the wing surface, turbulence can occur, leading to a complex flow regime. In such scenarios, Bernoulli's equation alone is insufficient to describe the aerodynamic forces acting on the wing accurately. Engineers must resort to more advanced methods. So the next is compressible flow. So compressible flow to fluid flow in which changes in fluid density occur and must be taken into account. This is particularly relevant in high-speed gas flows where variations in pressure, temperature, and velocity can cause significant changes in density. Unlike in compressible flow where density remains constant, compressible flow involves variations in density throughout the fluid field. Bernoulli's equation is derived under the assumption of incompressible flow where changes in fluid density are negligible. As a result, it is not valid for flows where density changes significantly, such as in incompressible flow regimes. In incompressible flow, variations in density directly impact the flow's behavior, altering the distribution of energy and pressure along the flow path. Therefore, Bernoulli's equation cannot accurately describe compressible flow conditions and requires modification or alternative approaches. So, for example, a high-speed jet engines involve compressible airflow due to the high velocities and temperatures associated with jet propulsion. As enters the engine intake at high speed, it undergoes compression, leading to changes in density, pressure, and temperature. In such compressible flow regimes, Bernoulli's equation alone is insufficient to describe the flow behavior accurately. So next, we have fluid energy losses. So in real-world fluid flow scenarios, energy losses occur due to the various factors including friction between the fluid and the boundaries of the conduit through which it flows as well as with the liquid itself. Additionally, heat transfer between the fluid and its surroundings can lead to further energy dissipation. These losses are typically attributed to the conservation of mechanical energy into thermal energy. The presence of energy losses complicates the analysis of fluid flow systems, particularly when using simplified models or equations such as the Bernoulli equation. While Bernoulli's equation assumes idealized conditions with no energy losses, real-world applications often involve energy dissipation mechanisms that cannot be ignored. Consequently, relying solely on Bernoulli's equation will lead to inaccurate predictions of pressure, velocity, and other flow parameters. So, for example, consider the flow of water through long pipelines used for water distribution or transportation. As water moves through the pipeline, it experiences frictional resistance against the inner walls of the conduit. This frictional resistance results in energy losses, leading to a decrease in pressure and velocity along the pipeline's length. Consequently, the pressure and velocity of the water at the pipeline outlet are lower than those at the inlet, affecting the overall performance of the system. So next, the application to non-streamlined paths. So when attempting to apply Bernoulli's equation between points that are not on the same streamline, it can lead to erroneous results. This is because Bernoulli's equation assumes that the flow is steady, invisible, and energy is conserved along a specific path. If the points are not on the same streamline, the flow conditions such as velocity and pressure may differ significantly, violating the assumption of the equation.
So for the derivation of Bernoulli's equation, let's first review the conservation of energy. So conservation of energy states that energy cannot be created nor destroyed, only transferred. So here we have the general equation of Bernoulli's equation. P here is the pressure of the fluid. The next term is just the kinetic energy. The rho is the density, and the v is the velocity. Next term is the potential energy. G is here is the gravitational force, and the H is just the elevation. The pressure energy of the fluid plus the kinetic energy of the fluid plus the potential energy of the fluid remains constant between both at stream. So next step, we introduce the concept of streamline. Gawa muna tayo ng diagram. So the streamline is a path followed by the fluid particles under steady flow conditions. Siya yung pinakadaan ng fluid particles. Siya yung trail. Siya yung sinusundan ng fluid particles. Siya yung pinakadaan. So in Bernoulli's, we assume that the fluid is in steady flow. So that the velocity will remain constant and the pressure will also remain constant. So next is our assumptions when it comes to Bernoulli's equation. So first assumption, we should assume that the fluid is incompressible, meaning the density of the fluid is constant and does not change with pressure or temperature. Next, the flow of the fluid is in steady flow state. The flow parameters such as velocity and pressure do not change over time at a given point in the system. So next, no friction losses. So it's a Bernoulli's equation na no friction losses. We considered the ideal fluid, which is ideal fluid is a fluid with no viscosity, resulting in no energy loss due to friction.
Okay, para mas maintindihan pa natin lalo yung mga sinasabi nila kanina sa mga naunang slides, let's try to consider yung pipe whose diameter and elevation change as fluid passes through it, which is itong nakikita nyo sa screen ngayon na diagram. Ngayon, i-prove natin lahat ng ito para mas maintindihan pa natin lalo. So, alam natin na ang work is equal siya sa force times a small amount ng length as displacement. So, let's represent it as delta x na lang. Makikita natin siya dito sa part na to. Not necessarily accurate, pero it's an assumption muna since wala naman tayong value na ilalagay. So, length niya is dito, x1. And since dalawang points ang kino-consider natin, point 1, and point 2, dito, meron na naman tayong displacement by x2, delta x2. Ngayon, so, makikita natin, since 2 points nga ang ino-observe natin, meron tayong force on each side. So, ang force dito is papasok since input natin siya. Now, force 1. Now, ang alam natin sa second part naman is meron tayong force na nag-go against sa una nating force na in-apply, which is yung work natin na in-apply nung una, meron tayong work na magre-result na nag-go against dun sa ating in-apply. So, ilagay natin as F2 going against. So, isusulat natin yan as F1 delta x minus F2 delta x2. Ngayon, maalala natin ang relationship ng force sa pressure. Sulat natin yon by pressure is equal to force over area, meaning makukuha natin yung pressure ay yung force by multiplying area and the pressure. Integrating it sa formula, P1 A1 delta x1 minus P2 A2 delta x2. Ngayon, alam natin na ang keep in mind yung ating thought na kung ano yung pumasok, yun din yung lalabas sa lahat ng all throughout Bernoulli equation natin. Ngayon, following that, yung volume, keep in mind na and masasabi natin na pag nag-multiply ka ng length sa area, which is yung area natin dito is yung cross-sectional area ng pipe, yung bilog ng pipe. Ito yun yung cross, ito banda yon. I-highlight lang natin. Ito and ito. Dito mo makukuha yung cross-sectional area ng pipe. Ngayon, pag nag-multiply ka ng length tsaka area, makukuha natin volume. So, input natin yon bago. So, P1 V1 minus P2 V2. But, alam natin na ang V1 at V2, yung sinabi ko kanina, kung anong volume yung pumasok, yun din yung lalabas, masasabi natin na pwede nating i-represent yun as V na lang. Kasi, same lang sila. Ngayon, ilalagay natin P1 minus P2, since ang pressure lang naman talaga ang nag-iba, times V lang. So, meron na tayong isang formula, isang equation na pwede nating ilagay sa Bernoulli equation. Next, ano pa ba ang mga kailangan natin? Since meron tayong involved na velocity, ibig sabihin meron tayong kinetic energy. Ngayon, solving for kinetic energy, KE, naalala natin, ang formula niya is 1/2 mass times velocity squared. Ngayon, alalahanin natin na ang mass, pwede natin siyang makuha by multiplying rho, which is the density, times the volume nung ating fluid. Ay, nung ating pipe pala. Now, having this, pwede nating gawing 1/2 rho V, which is volume, VO na lang ilagay ko, times velocity squared. Wait lang. But since dalawa ang ating points na ino-observe ulit, kailangan natin talagang ulitin gumawa ng dalawang equation for that, ng summation niyan. So, makukuha natin yung total kinetic energy by 1/2 rho volume times V2 minus V1, which is both yan na square. Alalahanin nyo, hindi dapat sa labas yung square. Kasi, iba ang magiging resulta nung nasa labas yung square sa nasa loob yung square. Okay? Since by PEMDAS. Okay? Now, meron na tayong another formula na kailangan natin para sa ating Bernoulli equation. Lastly, since pag may bago sa potential energy, meron ding probable na pagbabago sa potential energy niya. So, solving for potential energy naman, change ito pala. Change din to. Change din to. Yan. Lahat yan. Changing. Then, masasolve natin yung potential energy niya by having formula ng potential energy ay mass times G times H, right? Times height. Which is yung G is gravity, then mass. Now, since the 2 points ulit, gawin natin, and may pagbabago ng height since mag-elevate nga yung from point 1 to point 2, and walang magbabago sa iba, input natin yung rho V sa mass, rho times volume times gravity times H2 minus H1. Next, now nagkuha na natin yung formula ng potential, ng change in potential energy. Now, having all of that, applying the formula work is equal to kinetic energy plus potential energy, makukuha natin yung work is equal to kinetic energy, change in work, or total work plus potential energy. So, inputting all of it dyan, magiging P1 minus P2 V, which is volume, times 1 is equal to 1/2 rho V rho volume times V2 squared minus V1 squared plus rho volume gravity times height 2 minus height 1. Since ang mapapansin natin na lahat ng equation na nilagay natin, lahat ng terms ay merong volume nakakibat, we can divide all of it by its volume. Then makakancel out lahat ng volume. Now, mag-arrive tayo sa formula na P1 minus P2 is equal to 1/2 rho volume 2 minus volume 1 squared minus plus rho G H2 minus H1, which is similar sa ating formula dito. Ang pinagkaibahan lang, inequate sa dalawa. Pinag-equal yung dalawa. From the formula na work 1 is equal to work 2. Yan.
Here is an example of a Bernoulli's problem. Calculate the minimum pressure required to force the blood from the heart to the top of the head with a vertical distance of 0.5 meter. Assume the density of the blood to be 1040 kg per cubic meter. Friction is to be neglected. The given values are the vertical distance, which is H2 minus H1 is equal to 0.5 meter, and the density of the blood, which is 1040 kg per cubic meter. The required value is the minimum pressure required, or pressure 1 minus pressure 2. Solution: P sub 1 plus density multiplied by the gravity multiplied by H sub 1 plus 1/2 P V sub 1 squared is equal to P2 plus density multiplied by the gravity H sub 2 plus 1/2 P V sub 2 squared. If V2 is equal to V1, then P1 minus P2 is equal to the density multiplied by the gravity multiplied by the difference in the height plus 1/2 density multiplied by V sub 2 squared minus V sub 1 squared. So let's discard the other side of the equation because velocity is equal to each other, so it means na mag-zero siya. So P1 minus P2 is equal to 1040 multiplied by the gravity, which is 9.81, and the height difference, which is 0.5 meter. So calculating it, we will arrive with the value of 5101.2 Newton per meter squared.
So, we have a problem here. So, a horizontal nozzle reduces from 100 mm bore diameter at inlet to 50 mm at exit. It carries liquid at density 100 kg per meter cube at a rate of 0.05 meter cube per second. The pressure at the wide end is 500 kilopascal. Calculate the pressure at the narrow and neglecting friction. So, the first thing to do is to find the area. First, area 1. So, the diameter in area 1 is 100 millimeters. So, of course, the formula area is pi over 4d squared. So, that will give us 7.854 times 10 raised to negative 3 meters squared. Ganun din yung gagawin sa area 2. So, that will also give us 1.9635 times 10 raised to negative 3 meters squared. So, after that, we can get na the velocity. So, formula for velocity of course Q over A. So the flow versus over the area. So that will give us 6.366 meter per second. Ganon din sa B2, which results naman to 25.46 meter per second. So, applying Bernoulli's equation, makukuha na natin yung P2, which is 196 kilopascals.
Here's another example of Bernoulli equation problem. Water is circulating through a closed system of pipes in a 2-floor apartment. On the first floor, the water has a gauge pressure of 3.4 times 10 raised to the 5th power pascals and a speed of 2.1 meters per second. However, on the second floor, which is 4 meters higher, the speed of the water is 3.7 meters per second. The speeds are different because the pipe diameters are different. What is the gauge pressure of the water on the second floor? So, makikita naman natin dito sa right side of the presentation na meron tayong visual representation ng ating problem. Makikita natin dito sa V1 na part, yun yung first floor, and the V2 is the second floor. Next. So, to define the given, makikita pa rin naman kahit na hindi na natin tignan yung diagram, which is observe, but pwede naman natin ma-observe sa ating problem agad yung mga given, which is yung gauge pressure on the first floor, which is P1, velocity of the water on the first floor, V1, and the velocity in the second floor, V2. Dito naman sa height difference between two floors, since sinabi sa problem na 4 meters, yung second floor is 4 meters higher than the first floor, which is kung i-observe natin ng mabuti yung diagram, yung first point natin is mag-start sa first floor. It means yung height natin sa mismong point 1 is 0. Then it is 4 meters above papuntang second floor. Kung i-equate natin siya sa equation na H2 minus H1, 4 meters pa rin ang kakalabasan since wala ka namang ibabawas sa H2 mo, which is yung 4 meters. Like, 4 meters minus 0 is equal to 4 pa rin. Next is, yung hinahanap natin is gauge pressure on the second floor, which is P2. Yeah, it's observable naman sa ating problem. Next naman tayo. Okay. Water, 1, 2, 3. Applying Bernoulli equation. Sa Bernoulli equation natin na na-derive from last na mga presenters, pressure 1 plus 1/2 of 1/2 times rho velocity 1 squared plus rho gh1 is equal to pressure 2 plus 1/2 rho velocity 2 squared plus rho gh2. Manipulating it para makuha natin yung P2, since given naman almost lahat except for the pressure 2 lang. So, pressure 2 is equal to pressure 1 plus 1/2 of rho times velocity 1 squared minus velocity 2 squared plus rho times gravity and the height difference. So in solving, pag pinlog in natin lahat ng given, ang ilalabas dito is 3.4 times 10 raised to the 5th power plus 0.5 times 1,000 times 2.1 squared minus 3.7 squared minus 1,000 times 9.8 times 4, which is, respectively na given na din sa formula. Parang sinunod na natin yung formula. Kung alin yung nakatapat, yun yung mismong given. Next naman, bago natin makuha bago natin ma-add lahat, kailangan muna natin syempre ng pare-parehas na i-make sure na pare-parehas yung units ng ating mga ipag-a-add na terms. So, sa kinetic energy na part, since ang rho natin na given is 1,000 and ang 1,000 ang density ng water, which is ang unit niya is kilogram over meter over cubic meter, i-multiply natin siya sa squared units ng velocity, which is meters per second. So, given na magiging meters squared over second squared siya. Canceling out yung mga pwedeng makancel na units, magiging kilogram over meters times second squared na siya, which is equivalent siya sa unit of pressure na Pascal. Ganon din sa potential energy, mauulit lang din yung process. Now, nung sinalpak natin siya, sinimplify natin lahat, magiging 3.4 times 10 raised to the 5th power minus 4,640 minus 39,200 na lang. Lahat-lahat. Now, for the next step naman, inad lang natin lahat ng terms. So, magiging pressure 2 is equal to 3 times 10 raised to the 5th power pascals. And that is all naman. Note that nabigay kasi lahat ng energy like sa pressure, and involve ang pressure and velocity and ang potential energy natin. May height na given, may velocity na given, and may pressure na given. And especially, pressure din yung hinahanap. So, talagang involved yun sa ating Bernoulli equation. If there are cases pa na walang given na height and such, pwede nating i-assume na the potential energy is 0 na lang. So, ayan. Thank you.
Bernoulli's equation is a fundamental principle in fluid dynamics, expressing the conservation of mechanical energy in a fluid flow. Despite originating in the field of fluid mechanics, Bernoulli's equation has significant applications in electrical engineering. This interdisciplinary relevance highlights the importance of understanding and leveraging principles across different fields to solve complex engineering problems. The integration of knowledge from various disciplines is critical in modern engineering. Bernoulli's equation, while rooted in fluid dynamics, finds meaningful applications in electrical engineering through analogies and practical implementations. So, understanding the underlying principles of Bernoulli's equation can provide electrical engineers with valuable insights into the behavior of systems involving fluid flow, such as cooling mechanisms and measuring devices. One of the most critical applications of Bernoulli's equation in electrical engineering is in the design and optimization of cooling systems. Effective thermal management is essential for maintaining the performance and longevity of electronic components. Excessive heat can damage components and reduce their efficiency, leading to system failures. So, Bernoulli's equation helps engineers design cooling system where air or liquid is used to dissipate heat from electronic components. For example, in air cooling systems, understanding how airflow around heat sinks operates can be crucial. According to Bernoulli's principle, faster airflow over a surface decreases the pressure on that surface. This pressure differential enhances the cooling effect by increasing the heat transfer rate, which is crucial for maintaining optimal operating temperatures of electronic components. So similarly, in liquid cooling systems, Bernoulli's equation is used to ensure efficient coolant circulation, facilitating effective heat transfer from high temperature regions to the radiator. So by applying Bernoulli's principle, engineers can optimize the design of fans, ducts, and liquid paths to maximize cooling efficiency, ensuring proper flow rates and pressure drops for effective heat dissipation. Venturi meters, which measure the flow rate of fluids by exploiting pressure changes, are another example of Bernoulli's equation in action within electrical engineering. Accurate flow measurement is crucial for maintaining the efficiency and safety of cooling systems. Bernoulli's equation helps to relate the pressure difference in a Venturi meter to the velocity and flow rate of the coolant. Ensuring optimal flow rate is essential to prevent overheating and ensure that the components operate within their safe temperature range. This application also highlights the importance of precise control systems that regulate coolant flow based on the real-time measurements.
further understanding the relevance of Bernoulli's principle in practical engineering scenarios. So beyond cooling systems and flow measurements, Bernoulli's equation also influences electrical engineering through fluid electrical analogies. Electrical circuits can be analyzed using fluid flow analogies where voltage is analogous to pressure, current to flow rate, and resistance to flow resistance. For example, friction in pipes. So Bernoulli's principle helps in understanding how changes in pressure or the voltage can influence the flow or the current in a circuit. So these analogies extend to designing components such as transformers, inductors, and capacitors where magnetic field and fluid dynamics principles intersect. Moreover, understanding thermal effects in circuit where heat dissipation needs to be managed using principles similar to fluid flow further demonstrate the cross-disciplinary impact of Bernoulli equation. In general, the importance of Bernoulli equation in electrical engineering cannot be overstated. It provides crucial insights into the design and analysis of cooling systems, ensuring that electronic components operate efficiently and safely. Accurate flow measurements and the application of fluid electrical analogies illustrate how principles from fluid dynamics or mechanics can enhance the understanding and innovation in electrical engineering. Embracing interdisciplinary knowledge allows engineers to tackle complex problems more effectively, and that leads to more robust and innovative solutions. So as engineering continues to evolve, the integration of principles from different fields will remain essential in advancing technology and solving real-world challenges.